Good morning to you all. So we are now on the day 4. So time is going. Hope you guys are all enjoying. Weather is very good. And in the instrumentation and monitoring, again in the later portion also there is a lesson learned. There also I will focus on some of that things. So this one I am really focusing the inside. So why we are focusing inside? Because right now I am working on like where our client has 15 sites and each site is constantly monitored with the insert. So insert is now the norm. So everybody is doing that. I think in India, I have seen few articles because I always review, spend a lot of time in the insert. So I have seen also from India some monitoring going on the trailing sites. But anybody has heard about insert? I just want to know how many heard what is insert like. Means the name insert. You guys have heard that? Like you can. Yeah. How many of you heard about the insert? Like, no,
I have heard, but I don't know in detail.
Okay. No, but just name.
Yeah.
How many have heard about the name? Just raise your hands. Yeah. So, like you all know, like this insert. So definitely this will be important and it will be interesting to know what it is and why I give the you should know the concept because that helps. It's a very complex process. You will see, like when I will go with some theory, you see it's a very complex process and interpretation is important. It's like geophysics. You know that geophysics, what you are interpreting, that will be helpful. But if you are not able to interpret well, you cannot use those data. Same thing like I will mention when we go to the NISA because a new satellite is coming. It should be already there, but it's still delayed and the new date is in July. And that satellite is developed with NASA and ISRO. That's why that name of that satellite is NISA, NASA and ISRO. And I am involved in that project since 2000. So that there I thought that like if we know the concept a little bit, then when we interpret and you can again see that like you will get somebody is interpreting and give you a map. Like this is the ground subsidence map coming from the INSAR software. So, but when you see that, if you have some concept, then you can make your own interpretations because it is always site specific. It's not that the model give me this thing, I will just accept it. It is site specific and you have to see that. So there is a satellite, you can see that on the left there is a satellite. Okay, this is the satellite and this is the globe. So this is showing the path of the satellite. So the satellite is covering whole world. So we say that it's ascending and descending, like it goes from north to south, again come back from south to north. Why two different? Because the course is different. When you is descending, it is one path looking into a different direction, while ascending, it is again looking into a different direction because that's the antenna is taking the data. So the concept is like why we call it synthetic aperture. Like there is a synthetic aperture there, like the antenna, the mirror which is taking in. At the end, I will show you a video that will be more clear. And the satellite emits radar pulse. You can see that the satellite emits radar pulse, and radar pulse is backscattered, again going back. So that journey is emitting a ray, and that again coming back. So that ray can be different. It's not that it's a one amplitude, or their things can be different depending on what kind of product we are using. The amplitude and phase is the important. That is what is recorded. Amplitude and phase. So in the first, like when you are, say, whether you are in an ascending track or a descending track, you can come back to that same point at a certain time period. So, say in the first case, this is the first acquisition. That's what we call the phase 1, phi 1. And when we come back to the same site, it will take some time, and that depends on satellite to satellite. So when you came back to the next site, say there is some subsidence already occurred. Okay? Now that phase which is backscattered is phi 2. So definitely phi 2 is now different, because here you can see at least the length of the ray is more. So the difference between phi 2 and phi 1, we are interpreting it as the subsidence. That's what you see, the difference in the elevation. So this product is giving us the elevation exactly at that point, and when it comes back to the next time, what is the change in elevation. So this is a very simple thing, but if you see, the mathematics is highly complex. And this synthetic aperture, you can see how the area, one time how much area they are covering. That's why it's called the synthetic aperture. It's like magnified. So you are covering 5 kilometers instead of only 10 meters. That's magnification help you. You can cover 5 kilometers in one shot, like one picture. And the most important thing is this, the angle at which it hit the surface. That angle is very important in all the mathematical calculations. So you can see that the satellite is at a depth of, at the height of 780 kilometers. And this is the ground control range, how much area is covering, and this is the direction. And the velocity of satellite is 7.5 kilometer per second. So this is all physics. Based on this diagram, they will calculate what is the depth there. And this kind of thing, like what I am showing you now was in the beginning. When I started the INSAR and what is going on now, INSAR is completely different. Because that time we do not have that sophisticated softwares, and so with the advance of software, and you can see these right now the big like supercomputers can easily handle those large data, because these are very large data. That time it was not there. So what you see here is called interferogram. So what is the interferogram? This kind of picture is produced between the two sides. Like you say, they cover the 5 kilometer area, that is that area. In that area we will get this interferogram. And that interferogram is predicting how much subsidence is going on in that area. So the equation, you can see that you can solve it through the equations. And this is again the same thing like the wavelength. The wavelength is very important because that wavelength control how much it can measure. So between two time period like time 1 and time 2, it can only measure half of the wavelength. But this wavelength vary with what kind of ray we are doing. So there are like S waves, there are like X waves, there are like D waves, there are like L waves. We will show you. So what is interferometry? That's why INSAR is, it is a SAR like a radar, but IM is the interferometry. So interferometry is the phase difference of two complex SAR images. The SAR image also available in like the terrestrial, like a lot of the mines there, mostly the open pit mines, they monitor any movement putting a ground controlled radar. That's called SAR. Also airborne radar, that's also called SAR. But this INSAR is mostly coming from the satellite. But it is the same concept. But here you see the difference is calculated on taking account of lots also other things. What are the other things? The phi flat, because our earth is a rounded surface. So you have to flat it when you interpret it. You have to flat it. That's why again in the surface we have also topography. There is mountain, there is high-rise buildings, and there are a lot of things. That topography also has to be counted. So that has to be, those are the, what I am saying here, these are the, what is the things from the topography, what is things coming from the flat, like the geography. Then this is the movement part. So these are all error that has to be removed to get the actual movement. Then we have also atmospheric error. Then there will be noise. If you look into the GPS data, like again, I don't know how many you are involved in the GPS data, but I got involved in GPS data a lot. Even we see the GPS give us the value. Like again at a particular point, if you take the value every minute, you will find a difference there. Actually, there is no difference. So those are the noise. So you have to also identify the noise, identify the atmospheric error, and then find what is the actual movement. So the ground movement is calculated the phase, and you see we are showing that interferogram. For example, if there is a uplift, so it can be uplift or it can go down, same thing. So it says, like you will see, it is going from blue to red. So blue is the if it's going up, red is if it is going down. So you get this. These are like if it is very ideal like this, but in nature you don't see that kind of ideal thing. But this is an example. So here you see how many cycles are there, because each cycle is related to that half of the wavelength. So whatever data ray you are using, it is converted to half of that cycle. That's how we calculate how much subsidence has occurred. So the phase plus this is the number of cycle. Here n is the number of cycle. So SAR imaging used amplitude, and also the advantage of this radar is you can see through cloud. So weather is not affecting our data, because what was happening before this radar, we were collecting a lot of optical images also from the satellite, but those optical images we are missing everything if there is a cloud. In the night time we cannot get any data. But here it is 24/7. But I mentioned you, the surface, roughness and slope also control. So for other things, because this method is mainly people are using mostly for the earthquake and volcano activity. Ground subsidence is a very small part of the objective. But right now, I can give you an example. In 2008, the NASA, they had these conferences going on. Around 2008, on the ground subsidence, there was very few people who were working on it. But when next time I went there, 2015, I saw a full, like in a room, like there are like 300 people, everybody is working on the ground subsidence. So with time we see a lot of people are focusing on the ground subsidence. So you can see what kind of error, like that's why we call atmospheric noise, or sometimes the name is decorrelation. There can be decorrelation. One example is, like I showed you, like if you are in the ascending direction or in the descending direction. But you have a line of sight. Line of sight is the camera facing your slope. So if your slope is in the opposite direction, that what it is facing in the ear, but the slope is in the other side. So it will create a shadow image. So you will not be able to get the correct value. So these are called backscatter shadowing. So, and also there are some atmospheric noise. You can penetrate through cloud, but there are some atmospheric noise, we have to see that. So slopes that facing toward the satellite have good data. You can get good data from there. That's why when you see the data, you can ask them, is it from the ascending or descending? Then you look into like, what is your slope direction? So then you can tell them, no, my slope direction is this. So it's mostly, it goes north-south. So the camera faces east-west. So those east-west slopes are very important. But in other direction also, we can get that. And again, the decorrelation, major factor is the vegetation. So in a very vegetated area, you have to be careful. The data may not be good. Snow, flooding, water, it cannot penetrate water. So between time 1 to time 2, if your area is flooded, your all data is gone. Those data are garbage. That's why we see if our wavelength is longer, because that I mentioned you, that what is the wavelength? The longer wavelength is much better because it can penetrate also the vegetation layer. So here, that's what I was telling you. The line of sight, this is ascending, facing east. So east slope is good. Like again, the other side facing west, so west slope will be the best one. But any directions through mathematical, we all know how we can, with the vector diagram, we can solve anything if we have the data. So if you know the line of sight, and then actual directions, you should have some idea what exactly happening, that will give you the actual direction. So you can guide them. So that is my actual direction. Then knowing your line of sight and with the vector math, complex math, you can get also the real displacement along the real displacement. This is one example. You can see this is long time back. So that time only that what I am saying is called classical method. Right now what is going on is a lot of different method. But initially the classical method, this is the raw data you get. So this data is March 1997. Then on the same area we get another data which is September 2000. So we compare what is happening between these two time periods. This was my first data I analyzed. So you can see that along this there is a highway here. This is a 3D model, and you can see that highway also has gone down. And here you can see there are close to 20 centimeter. This one like very close to 20 centimeter of subsidence during that period. When this you can see how the interferogram, what I was mentioning, based on which we will collect the actual displacement. So this one, when this data first time came, people got completely surprised. 20 centimeter of subsidence has happened in the middle of the road. We didn't notice it, but later on we saw that, like again, we have to fix that road also. And if you see, when we did this analysis at a particular, the advantage of the INSAR is you can go back. How much? Because initially it started in 1991. But initially data is not, these data are not that high resolution. What data we are getting now? The resolution is much better now compared to then. But still, if you want to see the history of a site, you can go back to the 1991. The digital elevation model, DEM. You guys have heard about that? Yeah. So the digital elevation model is like how you model your topography. Initially, we send the surveyor, he goes there, give us some points, then we kind of interpolate those points and come up with our AutoCAD model. But the satellite is helping us. It is giving a much better model, especially in the mountainous. Definitely in the plain land, your surveyor data is good. But you send your surveyor, give me go and collect some point in the mountain, I will model your mountain. I don't think surveyor can do that. It's very difficult things to do. But this is helping us. And if you see that equations, there was a topography. So any data when interpreted, topography is a input parameter. So you should know what is the topography of that region. And we are also using these INSAR data to find the topography. That is one of the example. I have done that in the Grand Canyon. In US, in the Grand Canyon, you can see that we collected data from these two areas and we developed the digital elevation model. In this area, you can see that this is completely developed by the computer model. And in this area, you can see we have a flat surface, and it matched actually pretty well with the existing SRTM model, because our USGS time to time they go on do all using this kind of method and we call it the SRTM model. So you can see my company was then AMEC. So what we kind of match that data. So this method can be used for the DEM, and DEM also is a part of the interpretation of the subsidence. What kind of software this may be old version, but recently there are a lot of softwares available, and especially if you are using the European satellite data Sentinel, which is the best right now. Sentinel has their own software also, but you have to spend some time, like minimum 1 to 2 months needed to understand that and do the things, but you can use that. But I can recommend, this is the one model, this is actually the Sentinel one, you can use that. But the Gamma, this commercially the Gamma software, like I see the best. But I have also used another software developed by a company called Altamira, application part. So what we can see, ground subsidence, and also some of the erosion event, like you can even calculate if you have good data, like again not with the low resolution data. If you have high resolution data and that erosion gully is a large gully, then you can also interpret those erosion features. Landslides, that is the sinkhole, you can do that, and then the earthquake, volcanoes, I think they are the major part. 80% of the satellite data is mainly towards that, earthquake and volcano. Again, you can get also DM right now, the new satellite, and there is a Terasa, it's a private satellite, but they are mostly focusing, preparing the digital elevation model for the global. So you can get up to 1 meter resolution. But again, our LiDAR data, you can go up to 0.5 centimeter. They have capacity. But again, the LiDAR data, like those are mostly airborne data. Airborne data, you will do it locally. But again, this data is coming globally, so by sitting here, you can also analyze data from anywhere else in the world. Also, the vegetation mapping and the wetland delineation. I actually, because of the time, I am not showing that, but I have another slide also. Mainly I have worked on also how we can map the vegetation, what type of vegetation, also the wetland, I have done that. But now today we will mostly focus on what is our ground subsidence. So this is the, again, you can see that the 3D map of our whole Phoenix area. This is whole Metro Phoenix. All the areas covered here. You can do that, like a large area, you can prepare a map like that. This is one of my first project. I worked on the inside the mining. So what happened? Overnight in the mines, they saw that, you see that, okay? Overnight on the surface, they saw that. So, and there was a pipeline. It was going, this pipeline was the lifeline of that mines. So, that's why they invited us, and I worked a lot in this project, but again, these are all client confidential, I cannot go further. But I did work in that project for 20 years. Every year we have to we produce the annual subsidence map for that mines. So you can see that annual subsidence map. We produce that for that mines. Again, in another mines, you see that this is a open pit, and they have a crusher here. And the problem was, there was some high wall failure, and that failure was affecting the crosser. So their goal is where we relocate the crosser. So that's where you can see that crosser here. This crosser, they want to relocate the crosser. So definitely this is very helpful, because whatever survey data or any data is, you tell surveyor go there, collect the data, they will only go the collect the data where they see there is some movement is going on. Where there is no movement, no data. But the zero movement is also important. Like in this case, we have to see where is the zero movement, because if we are moving this crosser, we will have to move it to that area. So they have a lot of in the under this open pit mines, they have a lot of regime data. They have installed this regimes to collect the ground movement, and again we also compare what the INSAR is giving us to regime data. But again, the INSAR data, like, it is not a point data, but later on we are getting, now we are getting point data, but earlier it was not a point data. There was a, like, we assume a pixel, and all the data which is coming is the average of that pixel. Again, for one tailing dam, we did also all the things, like we analyzed their vegetation, and also we developed their DEM, and also we do the monitor their ground subsidence. And this tailing dam was, it has closed after the thing. So you can see this is the tailing dam. So this whole area we analyzed. This is the raw data. You see, this is the contour map, topographic contour we generated. You can see that this is the 3D model we developed, mainly based on the INSAR data. Now we also monitoring subsidence occurring in that area, where there was like very limited, less than 4-5 millimeter per year we are getting, so nothing to worry here. So this is an example, like you can do that. Coming to a landslide, I will show you some, like it's berries, sometimes mines, sometimes landslide. So this one I work with a state department. They have a highway. So the state department, they told us to, can we use INSAR data? Again, anything we start, we will have to start with the pilot project. So they gave me some funding for the pilot project, and we analyzed it here. And you can see that this is the highway. Along the highway, we also identified some of the areas where there is some landslide occurring. And in this particular data, when I presented in a conference, there was another consultant. They are actually part of, they have their own program, like INSAR processing program, and they do a lot of this kind of thing. They came to me and told me that we couldn't find anything there. How come you find that? So that's why the site knowledge is important. We were like engineers and geologists we have, and so they know where is it. So that's why we are able to manipulate the data and find it. Otherwise, you see how big area you are doing it. Focusing, the computer may miss it, because there is a process called filtering. And when you filter it, you use a lot of type of data filtering is used to remove the noise. Sometimes actual movement will be removed by that. So only difference between what they did and I did, the main difference was I didn't analyze initially we started with whole area, but in the whole area we couldn't see it. So we go to that local area and interpreted that data. That's where we saw that. But you should have the knowledge also. Where is that occurring? That's why I'm saying the site-specific knowledge is very important. In like one of the INSAR conference, we had like a big gathering and they wanted us to decide like, that was for myself, what kind of information we can put in our website. So a lot of people were thinking that put the ground subsidence in area because the user has no idea. So if you guys can put the ground subsidence, this is the ground subsidence we are interpreting between this time to this time, that will be good. In whole that like 200, 300 people, I stand up and told them, no, don't do that. Give them the first level data. When they go to the second level, they need the experts, site experts to interpret it. Then they all agreed. Because this can be error. There can be error and people will take that interpretation and go or do a lot of things. Here I wanted to show you, these are all coming from the classical method. In the classical method, we take the whole data and that's what I showed the interferogram. That method is now obsolete, only maybe me or my group is only using it because we know how to use it. But currently, the most people are focusing is this, which is called point scatter, because it is helping them because they are easily identifying those points automatically. But this method also, not that everything is good. But I have not worked much on this method, that's why I have not published any paper but I have a plan on to give a good guideline also on this method, but I have given in the classical method. But here you can see the same thing which we used using the classical method, we again switch to the point scatter method. Again you can see same areas also we are seeing the concentrated. These are the points and those points, like you see this more red is the more subsidence and then the green is the good and blue is again going up. So you will get that scale up to down and mostly the negative is the ground subsidence that are I focus. The up data, most of the time I ignore it unless if I am like in some cases we are also looking at the uplift. So what is the difference between these two methods? Again, why I still focus on the classical method? Because I am interested in tailings dam, correct? But what is happening surrounding the tailings dam also I am interested. If some area very close to tailings dams is doing something, I need to know that. Will it affect my tailings dam or not? You see? But this point scatter method only focus on the tailings dams. They don't go beyond that. But in the classical method, I get the whole data. That's why I focus it more. Again, this is more for a region without the vegetation was the issue. That's why people didn't like switch to point scatter. Because in the vegetation it's very difficult to get the data. You have to assume that this is the thickness of vegetation, then remove that and then interpret. It was very difficult. Again, it is suitable, like I mentioned, suitable for the monitoring adjacent areas of mining, what's going on there. Mainly the basin scale subsidence, like I showed you whole Phoenix area, like here you can see for your whole Dhanwad coal field area, you can see that. Again, it's not applicable for very again, it's applicable for the slow rate of movement. If your movement is fast, then this classical method also you can use that, because I told you between the time, the half of the wavelength only it can measure. If it is more than half of the wavelength, you will not get much data. It will be missed. So those are the things, that's why people were forced to, like right now, the norm is the point scatter. This classical method is kind of obsolete. Yeah. And also, your DM generation, you need that in your program. Coming to the point scatter, it is the discrete point. Like only the particular point you are getting the data. Not that between the points you are not getting any data. But again, you can generate million points. The computer is very good on that. Right now, when we started, we are getting only very few points. Now you can get million of points. But it is more suitable for monitoring. Like we are monitoring only daily scan. That's a very good one. And it can cover any rate. Very high rate, slow rate, doesn't matter. Also, vegetation or snow area. What? We use a corner reflector. It's called the corner reflector. That, like we put that above the snow level or above the vegetation layer. So that corner reflector can be tracked from the satellite. So satellite focus that, and that point we monitor that. So that's why that corner reflector is very helpful in those areas. And this is like earlier method, people have to interpret and spend a lot of time understand the site things. This is kind of AI. Take it, go with that. Only when I am involved, these people has to be redo. Otherwise, a lot of cases, nobody even understand that. Okay, they are giving me something, I'm happy with that. But this cost is high. But this sentence actually, I have to remove that right now with the development of highly developed model and things. It's not that expensive. Again, this is again another client confidential project, but we were the expert here in this project. In California, they are making a high-speed rail from south to north, like whole, almost 400 miles long. So mainly like their initial alignment was modified because of the ground subsidence. I cannot say anything beyond that. Because of the ground subsidence, what data we get when this is the data from between 2014 to 2016, they were planning that in 2012. So when 2016 revisited their plan, they have to change their. You can see that how much subsidence is going on between that two is like close to 35 inches in 2 years. And for the high-speed rail, because I had discussion with them, like you guys have Caltrans, which is like general railway. So why high-speed rail you do? But high-speed rail, the movement doesn't need any subsidence. subsidence can change a lot with the speed. Like when you cross a certain speed, there you will see how that very little change in the slope can affect. And also here, I will mention another thing we also did. Due to ground subsidence, is changing your drainage pattern. Because you have certain area when you do the surface groundwater model, the surface water model, you take the topography and develop your drainage plan. But if your subsidence, where you are thinking it will go out, if there is a ground subsidence, then it will go in. One example I can tell you, in one of our, in the near Phoenix, we had a US Air Force base. Between 1955 to 1991, there was 17 feet of ground surface. 17 feet. And people couldn't notice it because this is not happening right. It took like 1955 to 1991, during that period it happened. How we know that? Because they had a like a drain which was taking all the surface water outside the base. But in 1991 there was a flood in that area. During the flood they saw water is not going outside. Water is staying there. Then we again surveyed the channel, drainage channel, and that told us that 17 feet of ground. So that's why the surface water modeling, you have to take care of the ground subsidence. If it's area where some active ground subsidence is going on, you have to know that, and then this insert can help you a lot because it can clearly tell you what is the current, and also when you design. We don't design for the current, we design for the future. Like you have to know what will happen in next 20 years. So those kind of prediction we do. We tell them that this is our prediction based on the past data. So then we also modify the topography, and that can be used for the surface water model. This is one example. It is not exactly the satellite insert why I am focusing this data. You see, this is a similar data taken from a airborne method. So from a plane, but this is the data is exactly what will be collected using the NISA. So when NISA data will be available, definitely, because I heard that in the north, that I think in some areas there was a big ground subsidence going on, and some more, you know. That in the north, not Kedarnath, there was some marsh that I am, Josimot area, ground subsidence going on. They were building a tunnel that was closed. So this kind of data definitely can be helpful. So you can see here in that whole subsidence, like major neighborhood area we are monitoring, and clearly showing something going on here. The rest of the thing is good. Something going on here, then we can focus, go see those buildings, definitely they will have some crack there. So this is very helpful. Coming to again mining. This is one of the examples from we did for the tailings. So we can use that in the tailings dam. But for the tailings dam, let me make you clear. like I said, between one time period to the second time period, there should not be any change in the elevation. If in an active tailing facility, you are always changing the elevation, like you are building your dam and also putting the material in the pond. You are changing the elevation. In those cases, you have to be very cautious with this data. So you have to again ask them, because right now we are using sentinel data, and the sentinel data, the visit period is the time period is the 12 days. Like only either ascending or descending. But if you are taking both, it will be 6 days. In 6 days you can get one, but it will be coming from the other side. You have to again interpret and do some mathematical calculation to come up with something. But always I prefer either ascending or descending. I don't mix them. But again, the mixing is also important. But if you take one data, so every 12 days it's coming. So I have to make sure those areas I have not done anything to the ground surface in that 12 days. But if you do something, then you have to be cautious. What the interpretation, you can question that interpretation. So here you can see, we see a very big, large movement within 3 years of time period, close to 400, 500 millimeter of movement in that particular, like you can see that one point, because here each point can give you this plot. You click to the point, it will give you all the data. This is one of my favorite methods. It's called S-bus. S-bus insert. What is the, if you go back, you see we are, that is called a baseline. The concept of the baseline is, you have, like I said, you time 1 you have the satellite there, and time 2 satellite there. But it is not that satellite is at the same point when it was in the time 1. It's impossible. So always there is a baseline error. What is the baseline? Baseline is the satellite location at time 1 to time 2. So that baseline, if it is a small, you will get a better data. But if that baseline is large, then you will have to again question the data. That's why what we do, we found, like say in 2 years we are analyzing, there are so many data, every 12 days I am getting a data. But in that data, then I go and look into this baseline. So in that baseline, I found the smallest baseline. And to do a interferogram series, you need at least 7 to 8 such data. So those data are called S-bus insert. And they will give me the information, and that is much better than the in general what people are doing. Again, I thought that maybe this one published by this person, I am referring to it. I found I reviewed like 10 papers. It was maybe 3-4 years back. I reviewed 10 papers and found 4 papers, only out of 10, only 4 papers mentioned that yes, INSAR is giving us something. Rest of the 6 told that we couldn't find anything. So even if you have monitored the INSAR, still you cannot have get that. But this paper which I am showing you, they found something which I see, yes, the other people didn't find it like I mentioned it. I found it, but they didn't find it. So that's the things, how they are interpreting it, how they know this site. So here you can see that this movement, like they have data till 22nd and it happened in 2025. But you can see that the thing is going on, but initially they found this one is point scatter method, then another is S-bus method. Just seeing that, you can see that S-bus is giving me much better result than the point scatter. That is one thing I wanted to do. That's why I am presenting here. S-bus is definitely better. And you see both point scatter and S-bus very close to the failure, making a torque. It's not the actual movement, how much is happening. The trend is the important. Same thing with the pore pressure also. Both pore pressure and settlement look into the trend. If trend is showing it's accelerating, whether pore pressure or subsidence is accelerating, we see a change, then that's the cause. So you will have to be careful on that, like when you do that. Again, this is a concept that came, like you can see that this is in track, there are two tracks they are looking into. Track 155, again the one may be the going ascending, another may be a descending track. So this is the past movement, and you can see that they found some kind of subsidence in some areas, but this is a concept where they are collecting the inverse velocity. What the inverse velocity will tell you? If you can join it, at the time of failure you will have the zero edge. So you are going reverse. This can also predict where it will occur, and that's what they are saying. Like in one case, this is the location 6. Here they got a data which predicted that this one will fail exactly at that time where it occurred, like very close to the time of failure. So this is a new kind of things also. You can look at that. This is called inverse velocity that can predict when it is going to occur. So right now, so many agencies, and like again, this is the last one which is coming. We are waiting for that. But we have like European agencies, Japanese, Canadian, then these are Dutch, again these other private agencies is like Italian agencies, they are private. Then Korea also they have one. So many satellites are going on. Again, this TerraSAR is not mentioned here, but because they are completely private. So you can see the history when it started in 1992. The first one started. That the data I showed you for the Metro Phoenix is from that satellite. So then like so many satellites, and then every satellite has a lifetime. Not that it will continue forever. Every satellite has a lifetime. And then this Cosmo and TerraSAR, these are very important because they are very like high resolution data. So here I will show you what I was telling you, what kind of band they are like. Whether it is like the X band is 3 centimeter. You go to the C band is 5 centimeter. You go to the L band is 24 centimeter. And there is a S band is 12 centimeter. So the NISAR is, because when the NISAR was designed mostly by, I was involved also, so we recommended them use L band. Because the vegetation was affecting all our data. We We are focusing mostly like landslide areas and all those where we need those larger wavelength data. So in the NISAR they are using L band mostly for US, but from Indian side they wanted S band. So that's why they put both instruments there. So here I have a video, I hope it will. So this is how the NISAR, when operates, will be exactly same. That is the antenna. I was saying like synthetic aperture, magnified antenna. Okay, we can stop here.
Any questions?
First session.
On satellite.
Hopefully I answer one of your questions during my talk. Okay.
So these are data are available to all, or it is available to have to purchase?
Sentinel is free. Sentinel data is free, but you have to process it.
For processing, we need some special software.
You need some special software, correct. Like that's what I was showing you. Sentinel has their own also tool, but you have to learn that. But that Gamma software, that's available commercially. But again, you have to also learn that. You can buy it, but you have to even learn that. But there are like, I don't know in India there are companies are there or not, but people are planning. Because that's why once NISAR starts, in 5 years you will find a lot of IT people are in the modeling this thing. You will see that, I can predict that. That's what I am seeing in Europe and other places. Yeah. So I have worked with 2-3 different groups and they listen to me when I tell them, no, do this way, do that way, redo the modeling, don't use that, don't use this, because I have gone into all the details of this processing. Yeah.
So you said about this surface water modeling, right? So the surface water and this
Flood water modeling, both are the same, right?
Yeah, both are
Both the same, right?
Yeah, yeah. But like we call it the fraud, we say that it's a stormwater modeling. And regular surface water modeling, we call it a surface water. Because stormwater is a different they are. Because when you model the stormwater, I don't know how much people have involved, because in the stormwater you have to predict that PMP. That PMP is a statistical model. And how you do that, it's not that easy. Yeah. So, but in regular surface water modeling, you take the average rainfall and do that. But when it comes to the stormwater, you have to take the peak. Yeah, so that's. But the thing is, the surface, topographic you are considering, if it is an active subsidence area, then you have to use some model, because your topography is changing with time. So right now, like that's why I saw the one flood in the Chennai airport. That was designed very soon, means latest design, and that flood happened, I think, within 1 to 2 years, 2 years of time. That surprised me. Like they design it now, they should have used actually the original. I don't think the things have changed so much in the 1 to 2 years. But if their model, like they couldn't predict that, and still when the actual storm came, it flooded it. It should not have done that. So maybe due to two reasons, like whether the ground has subsided, then their model may not work, or what PMP they use now, the rainfall happened more than that. Like that is possible. Like what happened in the last time Pakistan, like that flood. That never ever happened in anybody's lifetime. So it was a very, very large event. So those kind of event very difficult to predict.
Any more questions here? Okay, then maybe we can move for a tea and we can come back and we can start the next lecture.